Well, we'll go ahead and get started. So we'll just hop into it. We'll have a quick introduction as to kind of who I am, and we'll have a little poll, and then we'll get right into Tacton product modeling. We'll actually do a demo. I'll show the environment. We'll actually start kind of building an example, and then we'll have time for some Q&A at the end. So, and I didn't change my title here, but so I was a technical solutions specialist. I've recently moved to the design automation department and will be a senior application engineer. I've got 20 years in manufacturing, mainly in two different areas. One in HVAC was the most recent, and in oil and gas, doing product design, QA, manufacturing engineering, and a host of other things. I've done a lot of design automation in that time as well. And just a quick little fun fact about myself. This is my wall of art and guitars, two of my passions. So all the pictures hanging on here, not these little pieces, but all these pictures are pieces of art I've created over the years. And as you can see, a lot of that art is inspired by guitars, and I've got plenty of guitars, so something I really enjoy there. So let's go ahead and we'll have a quick poll so we can kind of get a lay of the land here. So you should see that showing up here. And while everybody's looking and answering that, we'll just kind of get into it. While everybody has a chance to complete that poll. So just kind of a quick overview as to what Tacton is. So Tacton is really composed of two key modules. And there's a design automation module that has CAD integration. So it literally works directly within the CAD environment. And that is any CAD environment, whether that's, Inventor, Creo, or SolidWorks. Then you have a CPQ piece of it, which is a configure price quote module. It is a cloud-based module, and it's really for internal sales reps or internal sales reps, or even direct customer sales. I'm not going to go really into that piece of it because that's not really our focus today, but it does have live product visualization and augmented reality as a part of that. So let's get a quick poll result here. We not have the poll come up. Oh, here's our poll here.
Sorry, Josh, okay. Here's our poll.
No problem. So yeah, the question is have you used Tacton? So a few option here is maybe you've had some design automation experience, maybe in the CPQ environment, or have you used some other CPQ software? So give everyone just a minute to answer that. So looks like nobody here has used any of it. So that's probably a good thing, actually, because we're going to be starting pretty basic here. So that's good, because we will have further KVAs in which we will get deeper into this. So that way you can kind of come along with things as we go. So for a second here, we're going to talk about AI, and there's a really powerful example in Tacton in which we have a Sudoku puzzle, right? In Sudoku, in this particular example, there's 72 empty slots. And of course, you have 9 numbers that can go into any one of those slots. So the easy equation is 9 to the 72nd power of possible solutions to the Sudoku problem. And of course, I have here the incredibly large number, which I don't even know how to say, of possible solutions here, incredibly large. So to program something like that would be incredibly complex, hundreds to maybe even over 1,000 lines of code. I don't even know, but it would be incredibly massive. Not impossible, but huge. Well, with AI, and particularly Tacton's AI, it only requires 72 rules in order to solve this problem. And that's huge. And this is one of the key aspects of Tacton, right? There's lots of CPQ product modeling options out there. But the Tacton AI engine, which is what all this runs on, was developed at the Swedish Institute of Computer Science. And it has a unique ability, which is why it's patented, in that what you ultimately define are relationships. Rather than doing the typical if-then scenario, you simply define how one thing relates to another. And we're going to see some of that today as we build the model. So, a good realistic example of that is there was a Tacton customer. They had over 70,000 coded rules using the standard methods. It only took 150 rules in Tacton to produce the same result, right? So, and in addition to that, you get enhanced results, the ability to optimize. Maybe you want to optimize on performance versus price, or price versus performance, or weight, or whatever. You can optimize your results using this engine. So what is a product model then, right? We have this great AI engine. What can we do with it? Well, we built what is called a product model, which is really a collection of definitions that determine the product's limitations and interactions, right? And there's no 3D model necessary to model the product. Now, you can, with design automation, you can connect it to and automate a 3D model, but no 3D model is necessary in order to define a product. And we're going to kind of do that today. I'm a very visual person, so I am going to have a 3D model reference to look at so that we can kind of understand what we're going for, but it's not necessary. And this is also important because the product can be a physical product, but it can also be a non-physical product. It could be something such as a service offering, or something like insurance, for example, right? We could define the interactions and possible results of insurance, right? When you talk to your insurance salesman, right, you begin with, okay, are we talking about a auto insurance, a home insurance, a life insurance policy, a medical insurance policy, right? So that's kind of one level of possible options. Then you get deeper and you go, okay, this is an auto policy. Well, what type of vehicle are we talking about, right? What's the cost of that vehicle? What is the, or I should say market value of that vehicle, right? How many miles do you generally drive a year? All those types of things. Or do you wanting liability only? Are you wanting, how much, insurance are you wanting, right? These are all factors that ultimately define the product you will be sold, your insurance. And once again, that's a non-physical product that can all be captured in a product model. So kind of to go along with that, I've already kind of referenced this idea of layers, right? And so generally, you're going to have your technical rules, which in a 3D environment are, they can literally be dimensional rules, right? But then you may also have, marketing rules, right? Once again, what are we going to optimize on? Or what are we going to say, we're not going to sell this because we do so few of them that it really isn't cost effective to mess with our manufacturing floor. So although those are possible configurations, we're going to cut those out. You can have local rules, whether that's state regulations, or if you're selling across the world, they could be regulations based on what country it's going in. And then you can also have guided selling, once again, due to optimization, whether that's through, best price or best performance, things like that. And so all these things work together to produce a result. Kind of the way Tacton and the Tacton engine works is by defining relationships, it understands all the possible configurations of that product. So you kind of end up with an array of possibilities in which that product could be configured. But then as you begin to apply these rules to it, then the possible solutions get more narrow and more narrow. And as that product gets defined, even through customer selection, it gets even more narrow until you end up with a smaller array of possibilities. With that, you can then optimize within that. You go, okay, here's all the possibilities, but what's my lowest weight possibility? What's my best performance possibility? Or my shortest time delivery possibility? What's my lowest price possibility? Or I can just take a balance of them all and end up with this product, right? Now, of course, there's also the possibility of fully defining that product down to one result, right? By defining every possible selection through, the customer's selection possibility. But if, as in general, there's some openness there, and if there is, then we can provide these possible solutions as well and optimize based upon that. So hopefully with that, you get kind of a general overview of what the end result is and the engine that is behind it. But we're going to go ahead and hop in and actually begin to build a product model. So I'm actually going to be doing this in Tacton Studio. Okay, and this is outside of the CAD environment. However, I will hop over to CAD so that we can have a visual as to what we're actually doing and defining here. Let me organize my screen a little bit here because I need my reference so I can stay on track. Okay, so let's hop over to CAD here. So what we're actually going to be defining here is this simple palette, okay? And there's a number of options, and we're not going to get all the way through this example, but we can see here, right, the different options, how the different options interact, results, and apparently I have not finished this correctly. That did not size correctly. So good test, so I can fix that. Anyways, this is what we're going to be working with. And you can see here, we have pretty much the same environment here to work in. So this is the product model. And basically all I've done is after building this product model, I just have to associate the outputs to parameters in Inventor, right? And so it's literally just going, okay, once the, we'll hop in quick. This is where we're going to start. Once the length gets defined or once the width gets defined, just take that value and throw it into this parameter in Inventor, and boom, we're off to the races, right? However, we're going to stick in here because once again, we can do all this without CAD. Okay. So the first thing we're going to do here is we're going to define in here what's called the part structure. Basically, this is what pieces are necessary to create the assembly, right? So we're literally going to start by defining the top level. You'll see this is kind of similar to the way things are laid out in the Inventor model tree, or even the, any of the parametric modeling softwares, right? They kind of have a structure of part, subassembly, assembly, right? So we're going to do the same thing here. We have the top level assembly as a palette, and within that, we will have deck components. And you'll notice here, I'm not putting a space in the name. That's because this name will be referenced. And when you put a space, it can be done, but then you have to be careful. You got to have quotations, and it's just best practice to not have a space there. So we'll have deck components. We're going to have within that, we're going to have a deck board as a possibility, right? That we saw earlier, which I did not have constrained correctly in Inventor apparently. And we'll go back here and we're going to add a second part, which will be a deck panel, which is also a possibility for the deck. Then we'll hop back to the palette and we'll add a second part to this sub-level here, which is going to be stringer components. Okay, and those stringers are these pieces here. Okay, so hop back here. Okay, so at this point, we've kind of defined what pieces make up the palette and kind of their hierarchy, right? So the next thing we can do is we can actually start giving them attributes, okay? So for instance, a deck board has a length to it, right? So we're gonna provide that here. So we have a length is one attribute, and then we can set limits to that length. And this can be done in a couple of ways. One way is we can simply define it directly here, and I'll explain kind of the options here as well in just a second. But we could define that here by simply going, okay, 24 to 60 is an option. In this case, mainly because I know how I'm going to utilize this later, I'm going to leave it as an integer. We do have other options here as well. We have Boolean. We can define it as a float, which is basically we can have a large number of decimal places, or we can define it as a function. A function can literally, basically, it can be an equation or it can simply be text. It can be a number. So it's much more open. So I'm going to leave this as an integer, and I'm actually going to define its limits via a constraint. Okay. And once again, we're starting very simple here. So I'm going to add a constraint. And this is the window that comes up, and you can see it gives a lot of assistance here. And this is where this really makes the learning curve go very simple and very quick, right? So we'll start with length. And you can see we immediately get a different set of values or possibilities that we can continue on here. So I'm going to say the length, we're going to make it less, or I'm sorry, the length should be greater than or equal to 24. Okay. And I'll create a second constraint here. And we're going to say the length must be equal to or less than 60. So I've now defined limits here. Okay. And the other thing I can also do, which I'm actually going to remove, we'll do it somewhere else, but just want to show this here. We can define a default value and say, okay, I want, you know, when we initially run the model for it to start at a 48 value. So it will start at a 48 value, but it can then be adjusted. So that's kind of what that symbol means. I'm going to remove that because I'm going to do this a little different way later. So we're going to look at, let's see here. Give me a second to reference my notes, make sure I go the right direction here. Okay, so yeah, we're going to now create basically a user interface, okay, which is right here. We go to the execution tab and we're going to create an application. Now, by creating that, that also means we could have multiple applications for a single product, right? We might have one approach in which you just simply define dimensional limits, or we might have a separate approach in which it's based more upon the product that will be placed on the palette. So we have a different approach and different set of questions that is more for optimization. Okay, so we've now got an application. We'll give it an application name. Give me just a second here.
I think we lost your audio, Josh.
Oh, sorry. Okay, audio's back. Thanks for that. So we're going to call it palette. And we can add a step to that. And so we can have multiple steps. We'll kind of see what that looks later, hopefully, but we'll just call this first step size. Whoop, if I can type, size requirements. Okay. And then once again, the names I keep with no spaces. The description, we can do whatever we want. I'll add a space. We could make it whatever we want. That's what the end user will see, will be the description. So now that we've got our step, we're now going to add a, let's see, that's a search strategy. I think we can add it here now. Symbols are a little bit different. So let's hop back over to our part structure. We're gonna add this, and oh, I've got to add a group there. There it is. So I'll add it to that group. We'll hop back over here. So we've now got a group. We're gonna name that group size, or well, I'm sorry, we're gonna call that group size requirements. And actually, we're gonna back up here, and we'll actually call the step the palette configurator. So we've got palette configurator step, we've got size requirements, and within that, we now have the deck board length. Okay, so we've now got a user interface, and we will actually run this. Now, keep in mind, this is a very simple looking user interface. This is really a test environment. Okay, so this is not exactly how things would look in the CPQ environment. So keep that in mind. But we've got a deck board length here. Since we didn't define a default value, we've just starting out with 24 as the option. Of course, we can change that to 48. If we say go too far, we get a constraint issue, and cancel that, and it'll drop us back to our previous value. Okay, really simple, right? So let's get back in here and let's make things a little more interesting. So let's see here. We're going to go back to our part structure tab, and we're going to go at our palette level, and we're going to define a palette width, right? So we're going to take a look at our visual reference here. Let's shrink this. So we have a palette, right? Let's make this orthographic. We have this board that sits on top. We've defined a length for that board, and you'll notice that length is also the palette width. So we're going to define a palette width, and we're actually going to define that relationship, right? I talked about how we're defining relationships versus if-thens, right? Of course, an equal relationship by saying this is equal to this, that's very simple. It can be more complex than that. And we'll get into some of those things in future KBAs. But for now, since we're just starting out, we'll define a palette width attribute to the palette itself. And here's actually where I'm going to set the limits on that. And it's in this method, 60. And now we're going to set a constraint. And I'll use this button here. And we're going to say that the palette width is equal to our, notice I'll have to follow the hierarchy here, to our deck components. And the deck component we're going to set it equal to is the deck board and the length of that deck board. Okay, so we've now said that the deck board, which is a deck component, and its length must be equal to palette width. And you'll notice here I get a nice readout. The palette width equals the length of the deck board. All right, so once again, very helpful. So now we have that relationship, and what we're actually going to do, we're going to delete these because those limits have now been defined here at this level. Okay, so we're going to now throw this into our application. So I'm going to create a field from this attribute. I'm going to put it into our size requirements. So I now have a deck board length and I have a pallet width. And we'll correct that name or the description so that it'll make sense in our interaction there. And now what I'm going to do is this deck board length, I'm going to make it a read only. So it's just going to give us the result of that constraint. Okay. And so we'll just take a look at that, right? So we know they're equivalent, super simple. If I change this, deck board length changes. And this can be very helpful having these readouts so that although at the customer level, they may not need to see this information during testing, being able to see and make sure that the constraints that we've set are propagating appropriately, this is really helpful. So let's step back into our environment and continue on. So we are now going to move back to our part structure. And on the palette level, we're going to further define the palette here. So we've got a palette width. We're going to add the stringer spread, which is going to be the distance between each of those stringers. And we need to make that a float value because that could be, multiple decimal places deep. And then we're going to add a wing length. Okay, and we're going to leave that as an integer. Okay, and what that wing length is going to be a distance here. Okay, so in this example, this is what we're going for, right? I can change that wing length and it will shift. You'll notice here, I do not have a stringer spread value. That's because we're going to create a constraint that defines the relationship between the palette width and the wing length in order to determine what this value should be. Okay, so let's hop back over. Okay, so we've got our values there. And now we're going to create a domain. Okay, so for this wing length, you'll notice here I have some set options, right? It's not just whatever the customer puts in, right? We only allow for none, a 3-inch or a 6-inch wing is all we allow for. And you'll notice here as I do this too, as I change these options, I get these color changes. What that's telling me is that if I want this, then I'm going to have to change certain values. So this has to change to no, which is the 4-way entry, right? If I change, I don't think the wing, yeah. So if I want a 6-inch wing, I cannot have a pallet this small. Okay. And we will see that later as we build this model. So we've got a wing length here, and I need to set those options. So that can be done via creating domains. And you can see we already have an existing domain, which is simply your true or false statement, yes or no, right? And you'll notice they have a resulting value. In this case, it's simply a 0 or a 1. So we can either utilize the name result as a yes or no when creating our equations, or we can utilize a value. Right. And that's actually what we are going to do in this instant is utilize that value. So we're going to create a new domain. We're going to call this wing length. And within that, we're going to have wing none with a description of none and a value of 0. And this will actually be the dimensional value. So if the customer selects none, the dimensional value that gets fed is going to be 0. Then we have wing 3-inch, and we'll say 3-inch wing, and we'll give that a value of 3. And then a 6-inch wing, and of 6. Back over to our part structure. And with our wing length, we can now set that to utilize that domain. Okay, so let's go ahead and, well, rather than add it, we'll add it later, but that will give us this type of interaction. Okay, we'll do that here in just a minute. Okay, so we're now going to move to, or yeah, no, we'll go ahead and do that now. So we're going to create a field from that. We'll add it to our palette configurator, size requirements. Okay, so we now have a wing length, and we're going to remove this deck board length because we don't need it at this point, right? And we now have these two options. So we'll just go ahead and look at that real quick. Right. Not doing anything, but we can see how that works. So we'll step back to our parts structure, and we're going to move to stringer components, and we're actually going to need to add some parts to that. Okay, so we're going to have a left stringer, another one, right? We'll add a center stringer. Now you'll notice I have 3 here, but for my deck boards, I only defined 1, right? Even though I can have lots of deck boards. The reason I did that is because in this instance, and we may not get to this today, we probably won't, but in this instance, I would want the ability to go, okay, when the width gets to a certain smaller value, then that center stringer will be removed and no longer be active. So that's the reasoning behind that. Whereas in the deck boards, where that would basically, in Inventor, we would just call it an array, right? And here we'll have a value that defines the number of deck boards, and that value will shift and change. There's also, you'll notice there's this number of instances. There are things that can be done there too, right? In order to have the number of instances dynamically change. And then each one of those instances can then be further defined and have, for in this case, different lengths. Okay, but they're all going to be the same length. So we're going to take a slightly different approach. So in this left stringer, we're going to add a width value, and we're going to give it a static value of 1.5. Now we would, we can add that to make it dynamic later, but as of now, really it's a 2x4. And so the technical, instead of 2, it's technically 1.5 inches for a 2x4. So with that, we're gonna hop back to our palette, and we are going to, and I'm actually gonna add a group here. Okay. And this is just a nice way to organize our constraints. So as you can imagine, if you have something very complicated product, you could have a lot of constraints. So this is a good way to group them. So we're not going to have a whole lot. So I'm just going to call them, if I can type, constraints. And we can simply copy this, and we'll add a constraint within that folder, throw that in there. And we will create a new constraint. Okay. So in this constraint, what we're going to do is we're going to have the palette width. We're going to subtract 2 from that. And we'll hop back and I'll explain why we're creating this equation this way exactly. But we have a palette width. We're going to subtract 2 from it. And then we're going to multiply that by the wing length. And that is going to have to equal the stringer spread value plus the stringer components stringer width. So we have our nice readout here, which is the pallet width minus 2 times the wing length equals the stringer spread plus the width of the left stringer. Okay, so what I'm saying here is, let me give us a little visual here. Okay, so the width is right here of this 2x4, right, which we defined as 1.5 inches. Okay, so what we're saying is the spread between these parts plus the thickness has to equal the pallet width minus 2 times the wing length, okay, which would be this here, right? So that variation. So if we change that wing length, we're going to subtract it from the total pallet width, right? And we have to multiply that by 2 because we have 2 sides to it. Okay, so hopefully that makes sense to you guys. Throw this back to 0. Okay, and so yeah, we've already tested it there and looked at that result, but we can test it in this environment as well. And so if I change this to 3, we can see, let's see, that's not in here. Oh yeah, I have to add a value to be visible in this environment, which I haven't done. We saw that earlier. For the sake of time, we know how that works. We see the results here. So I'm not going to take time to do that. So we can move on to see kind of some of the other things that can be done. So something else we can do is, we saw how we can set a default value earlier via a constraint. We can also set a default value here, but it does act a little different. So if we have a wing length, we can change this commit to wing none. Okay, and so that will, in fact, for the sake of the example, we'll set it to 3 inch. Okay, so that when I run this, you'll see it will start with the 3 inch wing. Okay, now it's not going to affect this model because it's so simple, but when setting that default via the constraint, it's literally just going to set it that way first time out, and it doesn't constrain the model in any way. Okay, it literally just says start this. It can be anything else as long as it's within all the other defined constraints. In this case, what it's going to do is it's going to, and we'll set it that way initially, but if we have another value that conflicts with that, it can change, but when that conflict is removed, it will move back to this value. Okay, so particularly when it comes to defining those optimizations, we go, okay, rather than just a default value, we want this to be the value as often as possible. Okay, and that's kind of how that works. So we'll leave it at that. And then we're going to come back to our part structure, and we'll create a few more constraints here because this is really where the power is. So I want to give plenty of examples here. So we're going to add another constraint, and we're going to say that the stringer spread must be less than, or I'm sorry, greater than or equal to the pallet width times 0.06. And I'm getting that this is an invalid constraint, so I've done something wrong. Oh, it's because I can't type. 0.6. There we go. Okay, so once again, this stringer spread is the value between those stringers right here. And we're saying that has to be greater than or equal to the width of the palette times 0.06. So what this does is it prevents the stringers from getting too close to each other. Okay, so if that occurs, then what needs to happen is that center stringer is going to have to go away. Okay, and here, make sure I've got all my strengths. So let's see, we'll also create a constraint. We're going to add a default value of palette width is a default value of 48, right? We've talked about how that works. And we're going to, let's see, palette width. We already have that. Yeah, we already have that as a execution. So we have the palette width here. And once again, we're not really going to see any result here, but what that will do is we get small enough, it will remove that center stringer, right? Because remember, it's got to be, let's hop back to our equation here, our constraint, I should say. So for that, the distance between those two has to be greater than the width of the palette times a 0.06. And what that 0.06 is, it's taking into account dimensions here with the thickness of the stringer. That's the word I was looking for, stringer, right? Plus a little bit, right? So that that value is always greater, right? So if we increase it, we get our center one back so that that value continues to be greater. I might show one more little thing here. Yeah, so for that to actually happen, we do need to do one more thing. So we'll do this out and then we'll open up for questions. So we now have that constraint, but this still exists in essence, right? So how do we make that go away? So that's where we define an attribute, which we have, we'll call it state, and we will give it a Boolean value. And that can then be controlled, okay, via the result of this constraint, so that that will then become, instead of being yes, it will become a no, thereby making it inactive. And that is really only necessary for feeding that information to Inventor in order to make that visually go away. But as it stands, that would not be necessary without the Inventor environment. So we will end there so that we have some time for some questions and answers. Hopefully that gives you kind of a start as to how this gets built out and kind of how things work. And I will say, particularly coming from a program background where everything is if-thens, shifting that frame of thought can be kind of difficult, because I really want to come through and just do if-thens. Well, if it's less than this, then you're going to remove the center one. Well, we don't have to do that, because remember, Tacton understands, where's my PowerPoint here? Back up here. If you remember, Tacton understands all the possible iterations, right? So by defining that value, that the distance between those stringers must be less than the width, we have now just reduced the number of possibilities, right? And Tacton understands those possibilities. That's where that AI engine really comes in. A very simple example of where it comes in. but hopefully that was helpful. So with that, we'll stop there and open up for any questions that people may have.